In this video, we're going to learn about chemical bonding, specifically ionic and covalent. So ionic bonds are formed between metals and nonmetals, and covalent bonds are formed between nonmetals and more nonmetals, or there can be a metalloid involved with a nonmetal. An example of a metalloid with a nonmetal would be silicon tetrachloride, SiCl4. We could also have N2, covalently bonded. We can have also NO2. Notice there is no metal in any of these cases, but in the case of KCl, there is a metal, potassium, and there will be an ionic bond between potassium and chlorine. So in the case of covalent bonds, think cooperative sharing, right? There's sharing of electrons. In the case of, say, H2, we can say that there's a valence electron on hydrogen and a valence electron on another hydrogen, and they come together and they form a chemical bond, H2. And we're going to learn about Lewis structures at a later time, but this would be the Lewis structure for H2, where that line represents the bonding electrons. So with ionic bonds, electrons are fully transferred. So an example would be potassium to fluorine, and the fluorine has 7 valence electrons, and the potassium has 1. And so the potassium will transfer its valence electron to the fluorine, and we get a K+ ion and an F- ion. We know that potassium has 1 valence electron because it's in group 1, and we know that fluorine has 7 because it's in group 7. Now, I want to point out that whether something is ionic or covalent has to do with the electronegativities of the elements involved. You may recall that electronegativity is essentially how strongly an atom is able to pull the electrons towards itself when chemically bonded. So if we look at H2, hydrogen has an electronegativity of 2.1, and the other hydrogen also has an electronegativity of 2.1. So the electronegativity difference is 0. This is a covalent bond because neither atom is pulling electrons towards it more strongly than the other. In the case of ionic bonds, well, there's a full-on transfer, so we're expecting one atom to be a lot more electronegative than the other. Lo and behold, our fluorine has an electronegativity of 4.0, and our potassium has an electronegativity of 0.8. That difference is negative 3.2 in this direction. I could have flipped them and it would be 3.2. The important thing is that the difference has a magnitude of 3.2. And because fluorine is so much more electronegative than potassium, you get a full-on ionic bond. Now, I do want to point out that there's such a thing as a polar covalent bond as being distinguished from a nonpolar covalent bond. In the case of a nonpolar covalent bond, you pretty much have to have 2 of the same atom, like in the case of H2, where no atom is more electronegative than the other. But in the case of, let's say, HCl, so H to Cl, when we look at HCl, the electronegativity of H is still 2.1, so that's Cl. And if we look back here, the electronegativity of chlorine is 3.0. So 3.0, we get an electronegativity difference of 0.9, and well, that means that the electrons are not shared evenly entirely between the hydrogen and the chlorine. It means that the chlorine is pulling electron density towards it just a little bit more than the hydrogen is pulling electron density towards itself. And so this will make a polarized compound where the chlorine is a little bit partially negative and the hydrogen is partially positive. You may have learned in biology that water is polar, and that has to do with the fact that hydrogen has an electronegativity of 2.1 and oxygen has an electronegativity of 3.5. So that difference is 1.4, and we can say that water is very polar, hydrogen chloride is a little bit less so in the bonding, and you can tell from the electronegativity difference. So I do want to finally mention that there's such a thing as percent ionic character. Everything that we're talking about here is on a spectrum. Pure covalent means there is no difference in electronegativity among the atoms involved in bonding. So I'm going to add another point here at 0 and 0. 0% ionic when there's zero electronegativity difference. That's going to be like H2, could also be N2, Cl2, F2, whatever, diatomic. When you do have an electronegativity difference, as in the case of IBr, which is a small electronegativity difference, you'll get a small, slight percent ionic character. The bromide is going to be a little bit more partially negative, and the iodine will be a little bit partially positive, but not a lot. As we get to a bigger electronegativity difference, like in the case of HCl, which we knew was 0.9 as our difference, so that's going to be 0.9, we get to an ionic character of, I don't know, maybe around 20%. As we get to higher electronegativity difference, you can see that there's generally an increase in percent ionic character. It's not perfect, but it's pretty close. You do get a good trend as you get higher electronegativity difference among bonded atoms, you'll get a higher percentage ionic character. So I hope this video has been helpful to you. Again, think ionic bonding with metal-nonmetal, and if there is no metal involved, if it's just two nonmetals or a nonmetal and a metalloid, then just consider it covalent, just maybe more or less polar compared to something else. But I hope this video has been helpful. Please let me know if you have any feedback or comments or questions in the comment section below. Thank you very much.